Hi, my name is Pete Betts, and today I'm going to be talking about the Cretaceous Evolution of Zealandia and how it's dictated by congested subduction. I'd like to acknowledge my co-authors, Louis Moraci and Meghan from ANU, and Joe Whitaker from UTAS, and we've been working on this problem for a couple of years related to our ARC Discovery Grant. Congested subduction is caused when there is an interaction between buoyant lithosphere and a subducting trench, causing relatively localised instability and disruption along that convergent margin. An example of a buoyant lithosphere that might cause congested subduction includes an oceanic plateau or a microcontinent. Congested subduction locally affects many things, including trench geometry, subduction polarity, deformation modes in the overriding plate, mantle flow on either side of the subducting slab, and in extreme examples it can cause orocline formation along an accretionary margin. The margin along between the Pacific plate and the Australian plate is a complicated one. The northern part of the margin is characterised by free subduction, but as we go in towards Zealandia, what we see is a more complicated history, which records two stages of congested subduction. The first stage records the congested subduction between the Hikurangi Plateau and the eastern Gondwana margin, and the second stage is the present day configuration where the Chatham Rise and the Campbell Plateau are essentially locking up this margin here and causing the localised tectonics. Today in this talk we're going to focus on that first stage of congested subduction between the Hikurangi Plateau and east Gondwana margin. In a recent paper by Nick Mortimer from GNS in New Zealand, he articulated a tectonic model whereby the Hikurangi Plateau collided with the eastern margin of Gondwana. This collision triggered an instability which finally led to the breakup of Zealandia from East Gondwana and the opening of the Tasman Sea. Three stages of this model basically show a relatively stable subduction zone in Figure A, the collision of the Hikurangi Plateau onto the South Island of New Zealand in Figure B, and then finally leading to the opening of the Tasman Sea at about 80 million years. The feature of the Mortimer model is that the Tasman Sea opens up behind where the Hikurangi Plateau accretes along the margin where the South Island exists today. This observation is inconsistent with numerical models that we've run with respect to collision of ocean plateaus as well as microcontinents. The two movies that you can see here are two examples of seamount and plateau accretionary tectonics and related to congested subduction. And what you can see is that in the frontal zone of even a small plateau or a large plateau, is you get a significant amount of crustal shortening, and away from that collision zone you get trench rollback. We also see that same phenomena in microcontinent accretion models. This one's from Moraci et al. 2014, and what we see is that microcontinent collides, you get shortening in the overriding plate, you get lateral escape as material flows sideways, and this lateral escape is largely driven because there's rollback away from the collision front, creating that space behind there. In extreme examples, you will get an orocline that forms in behind the zone of microcontinent accretion. The take-home point in this slide is that the interpreted model of Mortimer is inconsistent with the observations that we would expect from a numerical model. This time-space plot shows the complexity of New Zealand tectonics from the early to middle Cretaceous, showing the detail of the geology that's there. And I don't expect anyone to look at this time-space plot except to see that there's been a significant amount of work in trying to synthesize this information and understand how it all ties together. I want to bring your attention to the South Island in the Westland and Canterbury plains, where there's been a significant amount of geochronology, and there appears to be two clusters of ages. One at about somewhere between 110 and 100 million years, and then again between 80 and 60 million years, sorry. And we think that these ages are significant. This slide shows a simplified version of the time-space plot showing the tectonic events that we think were happening at that in that period of collision of the Hikurangi Plateau. There are some key aspects to this. I've superimposed those two clusters of ages on that, but one of the things you see was that following the stable convergent margin setting, the South Island largely records extension related to subduction rollback, whereas the North Island records basically a collision. And we would argue that this is a critical observation. And as a result of that, we're proposing a subtly different tectonic model to that of Mortimer, and proposing that the Hikurangi Plateau actually collided with the North Island in its present day architecture, and that the South Island, that collision triggered extensional rollback in the South Island, leading and triggering the opening of the Tasman Sea. So a big implication of this is that we think that the collision of the Hikurangi Plateau was the major trigger for the opening of the Tasman Sea. The second cluster of ages, we think, are recording the collision between the Chatham Rise and the Hikurangi Plateau. And I'm going to show you how that works. And that happened as the Tasman Sea was opening. Then there was a period of hiatus and reconfiguration, and then subduction initiated again at about 25 million years. We're not going to talk about that. So how did that model work? This slide shows a comparison of the Mortimer model compared to our proposed model. The fundamental difference of the model is that we are proposing a collision between the Hikurangi Plateau and the stable margin of East Gondwana with the North Island of New Zealand, whereas the Mortimer model proposes that that collision occurred at the South Island. We believe that the geological record supports a North Island collision because there's continuous shortening in the overriding plate during the late Cretaceous in the North Island, and that collision triggers subduction rollback and extension in the overriding plate away from that collision zone, driving extension in the South Island, which is recorded by the metamorphic core complexes and other rift features, as well as the sinistral motion of the West Wishbone Ridge, which is related to the differential movement of the margin where there's trench advance and then rollback on to the south. In this stage of the model, between 90 million years and 80 million years, what we illustrate is the opening up of the Tasman Sea in response to the rollback of the South Island as it rifted off the margin of East Gondwana. We would argue that this is an asymmetrical rollback event of the Chatham and Campbell plateaus, and at the same time, to the north, there was also a rollback of the margin of East Gondwana, and this opened up a Banda Sea type setting in which the Northland ophiolites are preserved. An implication of this model is that there is continual segmentation along this ridge, driven by the West Wishbone Ridge, but also segmentation between the Northland ophiolite and the North Island of New Zealand and the Hikurangi Plateau. An important implication of this model is that extension is not triggered behind the colliding plateau as proposed by Nick, but is actually triggered by the collision of that plateau in response to congested subduction. The final stage of this model is when the rollback of the southern part of Zealandia continues until the subduction trench accretes and interacts with the southern margin of the Hikurangi Plateau. Once this system occurs, the margin shifts outboard and there's a stable configuration where the Zealandia is now located within the overriding plate. And this is the Cretaceous configuration of Zealandia, and it has been established by this point at about 60 million years. The Cretaceous geological record of New Zealand is complicated because it involves congested subduction. The present day tectonic models are not consistent with dynamic models, but we think we can overcome this inconsistency by explaining a model where the Hikurangi Plateau collided with the North Island, and the South Island and Northlands record a period of subduction rollback and extension in the overriding plate. There was a second phase of collision between southern Zealandia and the Hikurangi Plateau following this rollback event. We believe that this model that we're proposing is a mechanism to explain the opening of the Tasman Sea.